In the last two videos, we were talking about how to summarize a set of data. In one video, we talked about how to summarize a set of data with descriptive statistics, which are values that are calculated to summarize a set of data. We covered the measures of central tendency, which were the mean, median, and mode, and we covered the measures of dispersion, which were the range, mean absolute deviation, variance, and standard deviation. After covering the descriptive statistics, in the next video we covered how to summarize a set of data with graphs, with graphs and tables, and we covered how to make a bar graph for a column of qualitative data, and we covered how to create a histogram with a column of quantitative data. We also talked about how a histogram can also be presented as a table called a frequency distribution table. Each of these ways of summarizing a set of data that we've covered so far are meant to summarize only one column of data. And what I mean by that is, if we want to summarize this age column, this age column will have its own mean, median, and mode, and its own measures of dispersion, and its own histogram. And if we want to summarize the number of units column, we have to start all over again, because this number of units column will have its own mean, median, and mode, and measures of dispersion that need to be calculated, and it'll have its own histogram that needs to be created. And once we've summarized these two columns of data, once again, we have to start all over again if we want to summarize the number of children column, because if we want to summarize this column, we have to calculate a whole new set of descriptive statistics. We have to calculate another mean, median, and mode, and another variance and standard deviation. And we have to create another histogram to summarize this column of data. So all of the different techniques that we've covered so far are meant to summarize one column of data. And in this video, we'll actually talk about ways of summarizing two columns of data. And we'll start by covering a chart that can summarize two columns of data instead of just one column of data. And these ways of summarizing data that we've covered so far are all important. I'm not trying to say that just because they summarize one column of data means that they're not important. They actually are important, but we'll actually, in this video, I'm just saying we'll move on to ways of summarizing two columns of data, because in many situations it's also important to summarize two columns of data instead of just one. Let's talk about how to create a scatter plot. If we want to create a scatter plot, we have to choose two columns of data, and they have to both be quantitative, meaning we have to use two quantitative variables. We could start with creating a scatter plot for age and number of units. I'll move the histograms up higher so that we have more room to create the scatter plots. I said that our first scatter plot would be for age and number of units. So we need to make an x-axis and a y-axis to make a scatter plot. And we need to put one of our variables on the x-axis and one of our variables on the y-axis. It's really up to us which variable we want to put on the x-axis and which variable we want to put on the y-axis. Usually variables that have to do with amounts of time go on the x-axis, so we'll put age on the x-axis and number of units on the y-axis. So I'll put age right here. And we'll put number of units on the y-axis. when you see a scatter plot, you'll often see the title of the y-axis rotated. So it would be written vertically right here, but the software I'm using right now won't let me do that, so I'll just write it out this way. And we need to make tick marks on the x-axis and the y-axis. Age goes from 18 to 30, so we should probably use multiples of 5 on the x-axis, meaning we should go 0, 5, 10, 15, 20. That should give us a good number of tick marks. And we probably don't need to include 0 because a person's age can't be 0. And we need to go up to 40 because 40 is the highest age that we have recorded. And number of units in our data set goes from 12 to 15. So maybe we should use multiples of 3 because if we used multiples of 5, we would only have 3 tick marks. It would just be 5, 10, 15. And we want a few more tick marks than that, so let's go up by 3s. So it'll be 3, 6, 9, 12, 15. And we're going to plot each person on this scatter plot, and each person will be shown as one dot inside of the scatter plot. Let's start with person 1. Person 1 has an age of 18, and person 1 is taking 12 units, which means let's find out where 18 is on the x-axis. 18 is between 15 and 20, so 18 is about right here. And the person is taking 12 units, and that's right here on the y-axis. So we need to find out where 18 years old right here and 12 units right here meet up with each other inside of the scatter plot. So maybe we could put a dotted line right here above 18, above the age of 18, and keep going up until we reach 12 units. This 12 units is right here. And then we make a dot where they meet up with each other. So this dot is just showing that this person is 18 years old down here and is taking 12 units over here. And we don't include these dotted lines in the scatter plot. I just made them to show how this dot is lined up with this age down here and with this number of units over here. What about person 2? Person 2 is 30 years old and is taking 15 units. The age of 30 is right here, and 15 units is right here. So those meet up right here. This is 15 units. This is 30 years old. What about person 3 is 21 years old and is taking 12 units. So 21 years old is a little bit above 20, and 12 units is right here. So it's going to be right next to this dot, because they're both lined up with 12 on the y-axis. Person 5 is 40 years old, which is out here, and is taking 13 units. 13 units is a little bit above 12 right here on the y-axis. So let's move over from 13 until we get to 40. And this person is right here, about right there. And the last person is 21 years old, which is right here again. And this person is taking 13 units. So before we had a person who was 21 years old and was taking 12 units. Now we have a person who's 21 years old and is taking 13 units. Since they're both taking 21 units, they're both going to be at the same place on the x-axis, meaning these two, we're going to have two dots stacked above each other because they're both lined up with 21 down here. This person who's 21 years old will be lined up with 13 on the y-axis, which will be about right here. So both of these people are 21 years old down here, but this person is taking 12 units right here. This person is taking 13 units right here. So since this person is taking 13 units, they're a little bit above this person right here. We could also create a scatter plot for age and number of children. We could just take the x-axis we had for age and just copy and paste it. And then our y-axis is going to have number of children instead of number of units. And notice how number of children only has 3 values. I mean, it only has 3 different numbers inside of our data set. It only has 0, 1, and 2, which means that we're only going to have 3 tick marks. We could have more tick marks if we wanted to make decimals, like 0.5, 1, 1.5, but we'll just use the whole numbers. Let's make 0 right here, and then this would be 1, and this would be 2. So person 1 is 18 years old and has 2 children. So 18 is right here for age, and 2 children is right here. So we have to line up 18 years old with 2 children. And person 2 is 30 years old and has 2 children. So it'll be right here and right here. It'll be lined up with those 2 numbers. What about this person? This person is 21 years old and has 1 child. So here's 21, here's 1. We have a person who's 40 years old and has 0 children. That'll be right here. And we have a person who's 21 years old and has 0 children, which will be right here. Or about right there, because this looks like about 21 maybe. Now we have a scatter plot for age and number of units, and another scatter plot for age and number of children. And we can make one more scatter plot. And the last scatter plot we can make is number of units and number of children. I'll label the y-axis right here. Since it was number of children. So if you have 3 columns of quantitative data, you can make 3 scatter plots, because you have three different pairs that you can use. Remember, we can't make scatter plots with these two columns because they're not quantitative data. So maybe on the x-axis we'll put number of units, and then on the y-axis we'll put number of children. Remember, number of units only has three different numbers inside of our data set. We only have 0, 1, and 2, which means we'll only have 3 tick marks. And number of children, oh, I'm sorry, not number of units. I was thinking number of children. Number of children only has 0, 1, and 2, so it'll be on the y-axis. On the y-axis we'll have 0, 1, and 2, because there's only 3 different numbers inside this column. So number of children, 0, 1, and 2, because those are the only 3 numbers that appear in the column of data. Number of units. For number of units, we were going up by 3s over here, so let's do the same thing right here. 3, 6, 9, 12, 15. So person 1 has 12 units and 2 children, which would make their dot right here. Person 2 has 15 units and 2 children. They would be right here. Person 3 is taking 12 units and has 1 child. They would be right here. Person 4 is taking 13 units and has 0 children. 13 units is about right here, or maybe about right here, and 0 is up here for number of units. I mean, 0 children is right here, and 13 units is about down here. Then the next person is the same, so we actually have another dot right above this dot right here. So that finishes making the 3 scatter plots. Notice how when we were making histograms, each column of quantitative data had its own histogram. When you make scatter plots, each possible pair of quantitative variables has its own scatter plot. So this pair had its scatter plot, this pair had its scatter plot, and this pair had its scatter plot. When we were covering histograms, we talked about the different types of shapes that you can see in a histogram. We talked about the normal distribution, and we talked about skewness and kurtosis. Now we'll talk about the different types of shapes that you can see in a scatter plot. And the shapes that you can see in a scatter plot aren't the same shapes that you see in a histogram, because a scatter plot is showing 2 columns of data, and a histogram is showing 1 column of data. So in a scatter plot, you don't see a normal curve, you don't see a normal distribution, and you don't see skewness and kurtosis. You can only see those types of shapes by creating a histogram. The types of shapes that you see in a scatter plot actually have different names, and we'll cover those names right now. One type of shape that you might see in a scatter plot looks like this. You might see a shape in which the dots are rising as you go from left to right across the scatter plot. You might also see a shape like this, in which the dots drop or fall as you go from left to right across the scatter plot. You might also see a shape like this, in which the dots don't rise or fall as you go from left to right across the scatter plot. You might see a shape like this, in which the dots stay at the same level as you go from left to right across the scatter plot. This type of shape would be called a positive correlation. This type of shape would be called a negative correlation. And this type of shape would be called no correlation. So you can think of it this way. As the dots rise, if the dots rise from left to right, that's a positive correlation. So think of rising as being positive. If the dots drop from left to right, like this, it's a negative correlation. So when you think of negative, think of dropping, like this. And when you think of no correlation, just think of neither of these things are happening. The dots are just staying the same from left to right. Now let's look at some examples of some different types of scatter plots that might show a positive correlation, a negative correlation, or no correlation. Imagine that we were doing a survey and we were asking our participants how much driving they do per week and how much money they spend on gas per week. Once we finish our survey and we've collected our data, we create a scatter plot for number of miles driven per week and for amount of money spent on gas per week. Maybe our tick marks go up by 20s for number of miles driven per week. The tick marks that we would use would depend on what types of answers people gave us. But let's just say that these are our tick marks. And maybe for amount of money spent on gas, we're using tick marks of maybe $10. So maybe 10, 20, 30, 40. This might not be completely realistic, but I'm just trying to make a point about what the shape will look like in the scatter plot. Because I'm not exactly sure how much money a person driving 40 miles per week would spend on gas unless I did some more calculations. I'm really just going to make up some numbers. the main point that we're trying to make is just what the shape will look like in the scatter plot. Let's say that 3 of our participants tell us that they drive 20 miles per week. So since these 3 people are doing a fairly low amount of driving per week, they're not going to be spending very much money on gas, which means that they'll fall somewhere near the low end of the number line for amount of money spent on gas. They're not all going to fall at the exact same place, because those 3 people could be spending different amounts of money on gas, but all 3 of them will probably fall into the low area of the number line. So let's make up some dots for those 3 people. Let's say that they fall right here. So I'm saying that even though these 3 people are all driving 20 miles per week, they're not going to necessarily all be spending the exact same amount of money on gas, because this person down here might be, this person up here at the top might be spending more money on gas because this person's car gets lower mileage, lower miles per gallon, and this person here might have a car that gets a higher number of miles per gallon, which means that they don't have to spend as much money on gas, even though they're driving 20 miles per week. So up here at the top, we might have a person driving a car that gets lower miles per gallon, which means they spend more money on gas. And this person down here might be getting lower miles per gallon, which would mean that they would be spending, they would have a higher miles per gallon, which means that they would be spending less money on gas. And they're all in this low area where they're not spending much money on gas. What if 3 people tell us that they're driving 40 miles per week? Well, those 3 people won't necessarily all be spending the same amount of money on gas, because those 3 people might be driving different cars that get different miles per gallon. So they're not all going to necessarily be at the same place over here, but they're all going to probably fall into a similar range. And the range that they fall into will be a little bit higher than the range that these people fell into, because these people are driving 20 more miles per week, which means they'll be spending more money on gas than these 3 people typically. So the range is going to be shifted up. Maybe it'll be shifted from here up to here. And then if 3 people tell us they're driving 60 miles per week, they're going to fall into an even higher range for money spent on gas. They'll be spending more money on gas since they're doing more driving, so they might be up here somewhere. So the range is moving up again. And the type of shape that we're seeing right now is a positive correlation. If you have a positive correlation, it means that people who are higher on the x-axis are usually also higher on the y-axis. So people who are higher on the x-axis tend to also be higher on the y-axis. In other words, as x goes up, y tends to go up along with it. And it makes sense that this would have a positive correlation, because when people drive more miles per week, they spend more money on gas. So we would say that this data right here is showing a positive correlation between these 2 variables. In other words, it's showing a positive correlation between number of miles driven per week and amount of money spent on gas per week. What if we were doing a survey in which we were asking people how many credit card payments they missed this year? and what their credit scores are. Let's take a look at what that scatter plot might look like. And I'm not totally sure what types of tick marks we should make for credit scores, so I might just leave the tick marks blank. We'll just know that down here means lower credit scores and up here means higher credit scores. And higher credit scores are better than lower credit scores, so people up here would have better credit scores than people down here. Down here we have number of missed payments for this year. And when you miss more payments, your credit score goes down. So missing more payments will hurt your credit score. What that means is that if 3 people tell us that they've only missed 1 payment this year, then those people should have fairly good credit scores. I could have started at 0, but I started at 1. And if we have some other people who tell us that they missed 2 payments this year, those people will probably have lower credit scores because their credit score is going down because of missing more payments. So these people will fall down here into a lower range of lower credit scores. So these credit scores aren't as good as these credit scores over here. And if some people tell us they missed 3 payments this year, their credit scores will be at an even lower part of the number line because they'll have even worse credit scores. So the range of credit scores is getting shifted down each time we go up to a higher number of missed payments. And if some people tell us that they missed 4 payments this year, those participants would have even worse credit scores. So the credit scores would probably get even lower. I'm not an expert on credit scores, but I'm just trying to use this as an example. So my example might not be totally realistic. So we see a different type of shape here than we see over here. Over here we see that people who are missing more payments are having lower credit scores. So people who are further to the right on the x-axis tend to be lower on the y-axis. See how as x is going up, y is going down. So this would be called a negative correlation. This type of shape would be called a negative correlation. If you have a negative correlation, it means as x goes up, y tends to go down. Sometimes helps to make arrows to show this concept. So for a positive correlation, think of 2 rising arrows, meaning as x goes up, y tends to also go up. In my example, it was as miles driven per week goes up, amount of money spent on gas tends to also go up. So they go up together. If it's a negative correlation, it means that as x goes up, y tends to go down. So the two variables move in opposite directions. In this example, it was as number of missed payments goes up right here, credit score tends to go down over here. Now let's imagine that we were asking people for their shoe sizes and their IQs. We're doing a survey on shoe size and IQ. So maybe we'll put shoe size on the x-axis when we create the scatter plot, and we'll put IQ on the y-axis. And I think I won't make tick marks. I mean, I'll make tick marks, but I won't label them because the labels aren't actually important. It's really just the shape that matters. Well, maybe I will do them just in case it's helpful. Maybe we could start with a shoe size of 10 and then maybe 10.5. Let's say that 10 is the lowest possible shoe size. So this is 11.5, this is 12. Then we have 12.5. Maybe we'll stop at 13. And for IQ, maybe we'll, well, I'm not totally sure what tick marks we should make for IQ, so I won't label those. We'll just know that down here means lower IQs and up here means higher IQs. If some of our participants tell us that they have a shoe size of 10, we probably wouldn't really be able to predict what their IQs would be because shoe size and IQ aren't really don't really have much to do with each other, I don't think. I mean, I don't think that they're really related to each other. They could be, but I haven't heard of that, so we'll just have to make up some dots. Maybe let's just say that they're in the center. And let's say some other people tell us that they have a shoe size of 10.5. There probably won't be any reason for us to expect people with a shoe size of 10.5 to have higher IQs than people with a shoe size of 10. And there's also probably isn't a reason to expect for people with a shoe size of 10.5 to have lower IQs than the people with a shoe size of 10. So it could just be that it could just be that their IQs are the same as it could be that the people with the shoe size of 10.5 have about the same IQs as the people with a shoe size of 10. And it could be that people with a shoe size of 11 still have about the same IQ as the people with the smaller shoe sizes. So it could just end up being that as shoe size goes up, IQ doesn't go up or down. We might just see this type of a shape, kind of like a rectangle. This type of shape would be called no correlation. So this type of shape is showing no correlation between shoe size and IQ. What that means is it's it seems to be showing um, that it appears like shoe size and IQ have nothing to do with each other, because what it looks like is if your shoe size is higher, um, then what I mean is what it seems to be showing is people with higher shoe sizes don't really have higher or lower IQs than people with smaller shoe sizes. So, in other words, it looks like shoe size and IQ have nothing to do with each other, which means that we don't see any correlation in our data set between shoe size and IQ.
I chose some examples that were fairly obvious. I mean, it's obvious that there's a positive correlation between number of miles driven per week and amount of money spent on gas per week. It's obvious that the correlation would be positive, and it's also obvious that there would be a negative correlation between missed payments and credit score, because when you miss more payments, your credit score goes down. But in social science or psychology, there's a lot of examples that are less obvious, and you won't really have an idea of whether they're positively or negatively correlated unless you actually collect data and actually see what the data looks like. For example, if you're studying something like income and happiness, it might make sense that there would be a positive correlation in which people who are making more money are happier, but you wouldn't be allowed to make a claim that there's a positive correlation between income and happiness unless you actually collected a data set that showed evidence that that was true. Um, Also, in social science or psychology, you can't make a claim that two things aren't correlated with each other um, just because there's no reason to expect a correlation. For example, it doesn't seem like there would be any reason to expect a correlation between shoe size and IQ. There's no real reason to expect those two things to have something to do with each other. But if we actually collected data on shoe size and IQ, we might end up seeing a correlation between shoe size and IQ after all. Um, Sometimes a correlation that's unexpected will actually appear in the data. So before you can actually make a claim, you have to actually collect a data set that can show evidence to back up your claim. I wanted to talk a little bit about the definition of a correlation. Correlation is a relationship between two quantitative variables. That's the definition you'll usually hear for a correlation. And it's also a relationship in which a person's value on one variable is at least roughly predictable based on their person's value on the other variable. And I'll talk about what I mean by that. Let's say that a person has told me how many miles they drive per week, but they haven't told me how much money they spend on gas per week. Since a person has told me how many miles they drive per week, I can make at least a rough prediction about how much money they're spending on gas per week. Because if the person tells me they're driving 5 miles per week, I'll probably think, okay, well, that person probably isn't spending very much money on gas. If the person tells me that they're driving 100 miles per week or 200 miles per week, I'll think, okay, well, that person is probably spending more money on gas. So if the person tells me how much driving they're doing per week, I won't be able to predict exactly how much money they're spending on gas, but I'll be able to make at least a rough prediction of how much money they're spending on gas per week. The reason why I can make that rough prediction is because there's a correlation between number of miles driven per week and amount of money spent on gas per week. If a person tells me how many credit card payments they've missed this year, but that person hasn't told me his or her credit score, I can use the number of missed payments that they've had this year to make at least a rough prediction of what their credit score is. For example, if a person tells me that they've missed 0 payments this year, I'll think, okay, their credit score is probably pretty good. Their credit score is probably up at the high end up here. And if a person tells me that they've missed a large number of payments, for example, if a person tells me that they've missed 7 or 8 payments, I'll think, okay, well, that person's credit score is probably lower. It's probably not as good of a credit score. So since there's a correlation between number of missed credit card payments and credit score, you can use the number of credit card payments that a person has missed to make at least a rough prediction of what their credit score is. So if 2 variables are correlated, either with a positive correlation or a negative correlation, then a person's score on one variable is at least roughly predictable based on the person's score on the other variable. But if 2 things are not correlated with each other, then it's not possible to predict a person's score on one variable based on their score on the other variable. I've never heard of a correlation between shoe size and IQ, which means that if a person tells me that their shoe size is 10, and they don't tell me what their IQ is, I won't be able to use their shoe size to predict their IQ, because I don't know whether a person who has a shoe size of 10 should have a low IQ or a high IQ. If a person tells me that their shoe size is 13, that also won't be useful for predicting their IQ. So if you know that 2 things are correlated with each other, then it's possible to make these predictions. But if you're dealing with 2 variables such as shoe size and IQ, and it's never been demonstrated that there's a correlation between those 2 variables, then it's not possible to make a prediction.
I wanted to give some examples of some possible positive correlations and some possible negative correlations. It could be that there is a positive correlation between height and shoe size, because it could be that taller people have larger feet, which would mean that they would need to buy larger shoes. So it could be that as height goes up, shoe size goes up along with it, which would be a positive correlation. It could also be that there's a positive correlation between the number of children that people have and the amount of money that they spend on food per week, because when a person has a larger number of children, they need to spend a larger amount of money on food to feed all of the children that are living with them. It could also be that there's a positive correlation between the number of friends that a person has on Facebook and the number of photos that the person has posted on Facebook, because a person who has a larger number of friends on Facebook would want to share photos with all of those friends, which would mean that it could be that the more friends a person has on Facebook, the more photos they end up posting on Facebook. Let's try to also think of some examples of some possible negative correlations. You might think that there could be a negative correlation between the number of hours that a college student spends watching TV per week and the college student's GPA, because it seems like if a college student is watching more hours of TV per week, that they would be doing less studying and they would have a lower GPA. So it might seem like as the number of hours of TV watching goes up, the GPA goes down, but I've never actually read any studies on that, so I'm not sure if that's true. There might also be a negative correlation between commute distance, meaning the number of miles that a person has to travel to work or school each day, and the number of hours that a person sleeps at night, because when a person has a larger commute distance and they have to travel a larger distance to work or school, they probably have to get up earlier, which would mean that they would be getting less sleep at night. So it could be that as commute distance goes up, the number of hours of sleep goes down, which would be a negative correlation. There might also be a negative correlation between the number of miles that a person walks per week and the amount of money that a person spends on gas per week, because people who do more walking are probably doing less driving, which would mean that people who are doing more walking would be spending less money on gas. And if if the amount of money spent on gas goes down as the amount of walking goes up, then that would be a negative correlation.
Next, I wanted to go over the difference between a strong correlation and a weak correlation. A positive correlation can be weak or strong, and a negative correlation can also be weak or strong. If a correlation is a weak correlation, it means that the correlation is less consistent. It means that there's more participants who don't fit the overall pattern of the scatter plot. Let's think of an example that might be a weak positive correlation. What if we were recording income and account balance? We were recording how much money people make per year and how much money they have in the bank. Now, it might seem like that people with higher incomes would have higher account balances because if you make more money, it seems like you would be putting more money in the bank and you would have more money saved. But that might not be true for a lot of people because it also depends on how much money you're saving. If you have a person who's making a lot of money, but they spend a lot of money, then that person will have a low account balance even though they have a high income. So let's look at what this type of scatter plot might look like if we recorded the data. We might see um, a positive correlation in the scatter plot in which people tend to have more money saved when they have higher incomes. But we might also see a lot of people who are exceptions. What I mean is we might see a lot of people who don't fit this overall pattern. For example, we might have a lot of people who um, don't make very much money, but they have a lot of money saved because they're very good at saving money. So we could have some people up here in this corner area. So these people would have low incomes but high account balances, and we might have some people down here also. We might have some people with high incomes who spend a lot of money, and since they spend a lot of money, they don't have much money saved in the bank. They have low account balances. So we might have some of those people out here in this corner with high incomes and low account balances. So if we were recording income and account balance, we might expect to see something like this, in which we do sort of see a positive correlation in here, but there's also a lot of people who don't fit that pattern. There's a lot of people up here, and there's a lot of people down here also, which means that the overall pattern isn't as nice. It's not as consistent as it is down here. So this one would be called a weak positive correlation. this type of data set here would be showing a weak positive correlation. And I'm thinking that number of miles driven per week and amount of money spent on gas would be more of a strong correlation, meaning it would be more consistent, because if you drive more miles per week, you always spend more money on gas. So there aren't going to be very many people up here who don't do very much driving but still spend a lot of money on gas, because if you don't spend much, if you don't do very much driving, there isn't any reason to expect you to be spending a lot of money on gas up here. And if you do a lot of driving, you're almost definitely not going to be down here, meaning you're almost definitely not going to be spending only a little bit on gas if you're doing this much driving. So we're not going to have as many people in these corner areas down here and up here. So if you have more people in these corner areas here and here who are throwing off the correlation in the scatter plot, then you have a weaker correlation. But if people fall into this, if the people follow a line pretty closely, then it's a stronger correlation. And I'll show you what I mean by following a line. We could put a line in here to show that this is a positive correlation. So we could put a rising line in here to summarize the correlation that we see, meaning this is showing that as people drive more miles per week, they're spending more money on gas. And it's a positive correlation, which means this the line rises. So this is just a way of showing that we have a positive correlation. It's just kind of like a summary of the scatter plot. And if it's a strong correlation, people are following the line closely, meaning as this variable goes up, this variable goes up pretty consistently along with it. Not very many dots are far away from the line, but if you have a weak positive correlation, then the dots, even though the dots are overall rising from left to right, you have a lot more dots that are scattered far from the line, out here and out here, which makes it a weaker positive correlation. So I said I was thinking that this would probably be a strong positive correlation, meaning more consistent, and this one up here would probably be a weaker positive correlation, meaning it would be a lot less consistent. Let's try to think of an example that might be a weak negative correlation. I was thinking about maybe number of units that a college student takes and the amount of free time they have per week. Let's put number of units down here and free time up here. It seems like that college students who take more units would have less free time because they would be doing more studying or more homework, but that might not be true for a lot of people. So let's take a look at what the scatter plot might look like. You might sort of see a correlation in which the dots are dropping from left to right, but we're also going to have a lot more people who don't fit the pattern very well. So we could have a lot of people down here who aren't taking very many units, but still don't have very much free time, because your free time uh, is has to do with a lot more things. Or, I mean, it has to do with a lot of different things besides just how many units you're taking. It has to do with how many hours you're working per week and how many other responsibilities you have. So we could have a lot of people who aren't taking very many units, but since they're working so much, they don't have very much free time. So there probably are going to be a lot of people down here in this corner area. We could also have a lot of people up here who are taking a lot of units but still have a lot of free time. Maybe they're taking easy classes, or maybe they just don't do very much studying even though they're taking a lot of units. So maybe there could be a lot of people who are taking a lot of units, but they still have a lot of free time anyway. So we're going to have a lot of people in these corner areas probably, which means we'll probably have a lot of people who are far away from this line. If it's a negative correlation, then you would put a dropping line in the scatter plot. The line would drop from left to right, because this is showing that overall, people who take more units tend to have less free time. We can see that that's true with these dots in here, but there's also a lot of people who are far away from the line who don't follow this negative correlation. So this is, if this was the data set, then this would be showing a weak correlation between free time and number of units, meaning it's showing that as the number of units goes up, free time goes down, but it doesn't go down very consistently. What about number of missed payments and credit score? I'm thinking that this would be a more consistent correlation, or a stronger correlation, because as when people miss more credit payments, their credit score, at least I think, it almost always goes down. So if you miss more credit card payments, your credit score will go down pretty consistently. In other words, you probably aren't going to find many people down here who haven't had very many missed payments but still have low credit scores anyway. And you probably aren't going to find very many people up here who are missing a lot of payments but still have good credit scores. So we're not going to have, compared to up here, we're not going to have very many people in these corner areas. The people are going to be more closely following this line that drops from left to right, which means it'll be a stronger negative correlation. So I think this would be a strong negative correlation. And even if it's a strong correlation, we could still have a few people who don't fit the overall pattern. For example, I might have a participant who's driving a Hummer, and a Hummer gets very poor mileage, meaning it uses up a lot of gas. So that person would be spending a lot of money on gas, even if they're not doing very much driving. So I might have one person who's driving a car like a Hummer, and they're spending a lot of gas. I mean, they're spending a lot of money on gas up here and not doing very much driving. But if it's a strong correlation, I won't have as many of these people who stand out. There won't be as many of them. And if it's a weak correlation, then there'll be more people who stand out from the pattern and don't fit the overall pattern. So this would still be a fairly strong correlation, even if I just have one person out here who's not fitting the overall pattern. This one person wouldn't weaken the correlation very much. And next I wanted to show you a website that can help show you the difference between a weak and a strong correlation. It can actually show you the difference between negative and positive, and the difference between weak and strong. But first I wanted to give you some definitions for some of the concepts that we've covered. Before we go to the website. So a positive correlation is a correlation in which people with higher values on one variable tend to also have higher values on the other variable. So a positive correlation is something like miles driven per week and amount of money spent on gas, because in this case, people with higher values on this variable down here tend to also have higher values on this variable up here. So that would be a positive correlation. So a positive correlation means people with higher values on one variable tend to also have higher values on the other variable. A negative correlation is a correlation in which people with higher values on one variable tend to have lower values on the other variable. So this would be something like number of missed credit payments and credit score. People with higher values on number of missed payments tend to have lower values on credit score. So as one thing goes up, the other thing tends to go down. That's a negative correlation. We also talked about weak and strong correlations. A weak correlation is a correlation that is less consistent with more people who don't fit the overall pattern of the scatter plot. These are my two examples of weak correlations in which there's a lot of people in these corner areas who don't fit the overall pattern of the scatter plot. A strong correlation is a correlation that is more consistent and has fewer people who don't fit the overall pattern of the scatter plot. These were my two examples of possible strong correlations. So I said that if the dots closely hug this line, like they do here, then that's a strong correlation. And if they closely hug the line, like they do here, then that's also a strong correlation. I misspelled strong, but this is supposed to say strong correlation. Now let's go to that website that helps demonstrate these correlations. This website allows you to plug dots into the scatter plot, and it tells you what type of correlation you have. So if I make the dots closely follow the line like they are here, then that's a strong positive correlation. But if I put in a lot of dots that are far away from the line, like they are here, then it becomes a weak positive correlation. So you could think of it as the correlation becomes weaker, the scatter plot is kind of expanding out, and with more dots that are farther away from the line. So as the correlation is becoming weaker, it's kind of expanding like a balloon. It's kind of like you're blowing up a balloon. If the dots closely follow a line going down from left to right, then it's a strong negative correlation. But if I add in more dots that are further away from the line, it becomes a weaker negative. So now it's become a weak negative because now there's a lot of dots that don't follow the line very closely. And when it becomes a weaker negative, it's harder to even see that it's a negative correlation at all, because it's starting to look more and more like no correlation. So as it becomes weaker, the negative correlation becomes less and less obvious. And if the dots don't rise or fall from left to right, then it's no correlation. If the line is flat like this. And so if you have a positive correlation or a negative correlation, then the strength of the correlation depends on how far the dots are from the line. But if it's no correlation at all, then it actually doesn't matter how far the dots are from the line, because even if I add some dots down here and up here, it's still no correlation. So if there's no correlation, then it actually doesn't matter how close the dots are to the line. It's still just no correlation. For example, my main point is, even if the dots are really close to the line like they are here, it would still just be no correlation, because the dots aren't rising or falling from left or right. You wouldn't say that it's a strong no correlation, because there's no such thing as a strong no correlation. And next I'll talk about how there's actually a value that can be used to measure the strength of a correlation. There's a value called a correlation coefficient that can be calculated with the data set. And the correlation coefficient goes from, it can take on a value anywhere between -1 and +1, meaning the value has to be somewhere between -1 and +1. If the value comes out to 0, it means that the data is showing no correlation at all. And if the value comes out to a negative number, it means that the data set is showing a negative correlation. And if the value comes out to a positive number, it means that the data set is showing a positive correlation. And actually, if the value comes out further from 0 and closer to -1, it means that the data set is showing a stronger negative correlation. And the value further from 0 and closer to +1 is showing a stronger positive correlation. And 0 is just no correlation. If it comes out to -1, it means that the data set is showing a perfect negative correlation. And if it comes out to +1, it means that the data is showing a perfect positive correlation. And I'll show you what a perfect negative and a perfect positive would look like. I'll go back to the website. If the dots perfectly follow a rising line from left to right, then the data set has a perfect positive correlation. This would be a perfect positive correlation. Something that might show a perfect positive correlation is age and the number of birthdays that a person has celebrated in his or her lifetime. So age and total number of birthdays celebrated would be a perfect positive correlation, because every time a person gets 1 year older, they've had one more birthday. So the line would look like this for age and total number of birthdays. And when the data set has a perfect positive correlation like this, then the correlation coefficient comes out to +1. You have a perfect negative correlation when the dots perfectly follow a line that drops from left to right. So this would be a perfect negative correlation. And something that would have a perfect negative correlation is the number of hours that a person is awake per day and the number of hours that a person is asleep per day. Because let's say we have hours awake down here and hours asleep up here. Every time a person is awake 1 more hour per day, it means that they're asleep 1 fewer hour per day. Meaning, if I sleep 8 hours per day, then I'm awake 16 hours per day. And if I sleep 9 hours per day, I'm awake 15 hours per day. And if I sleep 10 hours per day, I'm awake 14 hours per day. So every time the number of hours that I'm asleep goes up by 1, the number of hours that I'm awake per day goes down by 1, which means it follows a line like this, and it's a perfect negative correlation. If your data set has a perfect negative correlation, then the correlation coefficient is -1. Let's look back at this number line. So a data set on age and number of birthdays celebrated during a person's lifetime would give you a correlation coefficient of +1. A data set on number of hours awake per day and number of hours asleep per day would give you a correlation coefficient of -1. Because this one is a perfect positive correlation, this one is a perfect negative correlation. And let's think about where some of those other examples we talked about earlier would fall. I said that we would expect income and account balance to probably be a weak positive correlation. So since it's a weak positive correlation, it would come out at the positive end, but closer to 0, maybe right here. And we said that we would expect the number of units a college student takes and the number of hours of free time that a college student has per week to have a weak negative correlation. So that correlation of units and free time might be about right here. So these are fairly close to 0, which means that they're fairly weak correlations. This one was income and account balance, and this one was units and free time. We said that we would expect number of miles driven per week and number of dollars spent on gas per week to be a stronger positive correlation. We expected it to be a stronger positive correlation than income and account balance. So miles driven per week and amount of money spent on gas per week might be out here somewhere, closer to +1, since it's a stronger positive correlation. And we said we would expect number of missed credit card payments and credit card debt to be a stronger negative correlation. We said we would expect that to be a stronger negative correlation than units and free time. So since number of missed payments and credit score would be a stronger negative correlation, it would be further out toward -1. So it might be out here somewhere. So we have the two weaker correlations, the weaker positive and the weaker negative, closer to 0 right here. We have the stronger positive and the stronger negative out here further from 0. And we have the perfect positive and the perfect negative out here at -1 and at +1 and -1, which is the farthest from 0 a correlation coefficient can be. And this value that I'm talking about that tells you how strong the correlation is called a correlation coefficient. And they use the letter R to stand for the correlation coefficient. So if you see something that says R equals 0.74, then that would mean that the correlation coefficient is 0.74 because the letter R stands for correlation coefficient. And now I'll go back to the website to actually show you a demonstration of the correlation coefficient. There's another graph down here that can do it. Here we have a data set, and we can set the correlation coefficient, which is the letter R, to a certain number, and it'll show us what that data set would look like. This is a data set with a correlation coefficient of 0. So this is pretty much no correlation because the dots aren't rising or falling from left to right. And as we move up closer to 1, we're seeing a stronger and stronger positive correlation. So this is getting stronger and stronger. It still says weak because down here it still says weak because the dots are still pretty far from the line. Sorry. It looks like the dots are still pretty far from the line, so it's still pretty weak. But as we move up toward 1, it's getting stronger and stronger. And once we get to 1, that's a perfect positive, which is as strong as it can possibly be. Then once we move back down to 0, we're getting weaker and weaker positive correlations. And then 0 is no correlation, which is as weak as it could possibly be. And then as we move down toward -1, we're getting to see stronger and stronger negative correlations. And once you get to -1, it's a perfect negative correlation, which is as strong as it can possibly be. You can't have a negative correlation that's any stronger than this. Next, I'll show you some examples of calculating a correlation coefficient with Excel. This is the data set that we were looking at in one of the other videos. It's just a data set with some made up data values. And I showed you how to calculate all of these values with these 3 columns of data. And I didn't explain the values for skewness and kurtosis, meaning I didn't show you how to calculate those values by hand, because I just wanted you to understand the idea behind what those values are showing. The same thing is true for correlation coefficient, meaning I'm not going to show you how to calculate a correlation coefficient by hand, but I just want you to understand the idea behind a correlation coefficient. There is a formula that can be used to calculate it by hand, but we won't use that formula in this class. Just like how we aren't using the formulas that would be used to calculate skewness and kurtosis by hand. Each of these values, all the way up to kurtosis, are calculated with 1 column of data, meaning when Excel calculated these values for the age column, it took these 5 numbers in the age column and plugged them into different formulas to calculate all of these values, all the way down to kurtosis. When you calculate a correlation coefficient, you're actually plugging 2 columns of data into a formula. So we could ask Excel to calculate the correlation coefficient for age and number of units, and it would plug in all 10 numbers into a certain formula to give us the correlation coefficient for age and number of units. So let's do that. To get the correlation coefficient, we type in equals CORREL, put a parentheses, and it says array 1 and array 2. We can highlight age for array 1, then we need to put a comma, then we can highlight number of units for array 2, and then close the parentheses, press enter. It gives us a correlation coefficient of positive 0.47, and that's a positive number, which means that in this data set we have a positive correlation between these 2 variables. Let's make a scatter plot to show that it actually is a positive correlation. We can highlight these numbers and then go up to insert. You can't see what I'm doing, but I'm going to create a scatter plot. So it is somewhat of a positive correlation, because right here we can see that the dots are rising from left to right. This dot over here is more of an exception to the pattern. We can also create the correlation coefficient for age and number of children. So let's calculate that correlation coefficient. I'll put the one for age and number of children in here. So equals CORREL. Highlight this column, put a comma, and highlight this column, and it'll plug these 10 numbers into the correlation coefficient formula. We get negative 0.36, which means in this data set we have a negative correlation between these two variables of age and number of children. Let's make a scatter plot to see if it looks like a negative correlation. So it's really hard to see any pattern, but the value is saying that this is a negative correlation. I guess it's because maybe here you can see maybe these dots are dropping from left to right. It's probably a fairly weak negative correlation, which means it's very difficult to actually see that it's a negative correlation. What about we could do a correlation coefficient between number of units and number of children for this last pair of variables. And it comes out to 0.20. So it comes out to a positive number, so there's a positive correlation between age and number of children in this data set. Let's go back to this slide right here. And I'm going to mark off where these values came out to. First I need to finish this number line. Let's mark off these correlation coefficients. The correlation coefficient for age and number of units came out to 0.47, which is right here. Or it's about right there. The correlation coefficient for age and number of children was negative 0.36, which is about right here. And the correlation coefficient for number of units and number of children was 0.20, which is about right here. 0.2 is the same thing as 0.20. So let's focus on these two positive correlations for a second. One of them was for age and number of units, and one was for age and number of children. No, I'm sorry. This one was for age and units. This one was for units and children. Let me check that again. So the correlation between age and units was a stronger positive correlation than the correlation between units and children, because this correlation came out closer to 1, and this one came out closer to 0. The one that comes out closer to positive 1 is stronger. Now let's look at what the negative correlation came out to. It came out to negative 0.36. Let's compare these two correlation coefficients. And let's think about which one is stronger. Actually, the one that's further from 0 is stronger, so this one is actually stronger than this one over here. The negative 0.36 is actually a stronger correlation than the positive 0.20, because the strength is just how far it is from 0. So if you want to know which one is stronger, just ignore the negative sign, and then just look at which one is the bigger number, and that'll tell you which one is stronger. So for example, negative 0.70 or negative 0.7 would be stronger than positive 0.3, because negative 0.7 is further from 0, and positive 0.3 is closer to 0. So my main point is, if you have a negative correlation and a positive correlation, it doesn't mean that the negative correlation has to be weaker than the positive correlation. So negative doesn't mean the same thing as weak. A lot of people might tend to think that a negative correlation means weak and a positive correlation means strong, but that's not true. The strength is actually the distance from 0. And there's actually some guidelines for what's considered weak and what's considered strong. I'll put these guidelines on the screen. These are just rough guidelines. Anything between 0 and 0.4 would be a weak positive. Anything between 0.4 and 0.7 would be a medium positive. And anything between 0.7 and 1 would be a strong positive. Anything between 0 and negative 0.4 would be a weak negative. Anything between negative 0.4 and negative 0.7 would be a medium negative. Anything between negative 0.7 and negative 1 would be a strong negative. So notice how these numbers over here match up with these numbers over here. So at the positive end of the number line, between 0.4 and 0.7 is a medium positive, and at the negative end of the number line, between negative 0.4 and negative 0.7 is a medium negative. And we can see that as we go further from 0 up here, we're moving up to, from a weak positive to a medium positive to a strong positive as we get closer to +1. In this direction, we're moving from a weak negative to a medium negative to a strong negative as we're getting closer to -1. And -1 is a perfect negative, which means a negative correlation can't be any stronger than -1. And +1 is a perfect positive, which means a positive correlation can't be any stronger than +1. So it's actually not possible to get a correlation coefficient beyond -1 out here or beyond +1 out here.